And greetings, friends. We're here for our final day of 4C in the spring. So we're going to start off with a PLC. Now, I think I mentioned this last time, that I had put up a PLC, but then I realized I've already given you a traffic light. So I gotta make a different one that you can do. And so I'll do that, and we'll have that due Friday as usual. Homework 7, I hope you're working on that, and maybe keep an eye out for an answer sheet, which I'll post for the remaining ones that don't have, because some of them I put the answers right in there. And then our final is next Wednesday, which is the 20th, and it's, as usual, open during the day. It's probably look for a time of about 3 to 3.5 hours in order to do whatever it is that you need to do on that. And the usual requirements in terms of no working with people, no working with outside resources, things done closed book, closed notes, all that kind of stuff. And with that being said, this is our last official class, so I'll go over a couple of things today in terms of some of the extra wave function plotting, some of the radioactivity stuff, and then probably a few thoughts on the final, and then probably be just about finished off. So we'll go from there. Last time we were talking about the one-dimensional infinitely high well, infinite. And we had come up with a, well, we were developing a set of wave functions that worked inside the potential well, in which this went up to plus infinity up here and out, right? Whereas this down here was a u equal to 0. And we were developing a set of wave functions that worked in this space. And we were finding that we had only the sine versions, and that the cosine was not going to be applicable in this case, because we needed to force the wave function to go to 0 at the ends of the well here and here. So that led us to being able to sketch out, well, hey, we've got a couple of possible wave functions that right, like so, 1, 2, and 3, say, whereby the square of the wave function is the thing that tells us the probability of finding the particle at a given region, or within a given region. All right, so the key here, there's two pieces that are coming out of this. One of them is that probability is proportional to the square of the wave function times a particular region, right? So typically you're going to say, well, I'd like to find the probability of the particle being between here and here in the n equals 2 state, right? And so you'd say, okay, well, I'm going to integrate that and square it and integrate it, add up the individual slices, etc. We're just going to use the peak height to give us information about what is more probable and what is less probable. So where the peaks are is where things are more probable to happen, and where the peaks are, or should I say, where the zeros are where things are much less likely to be happening. So I noted this last time. You're going to look at a 0 here, and there's a 0 in the a couple of places here. So that is an indication that we are expecting not to find the particle at that point. Okay, so at these particular zeros. When you're thinking about the ups and downs of the wave function, those are not physically meaningful because ultimately probability, we're going to square it anyways. So even if you have a dip down here in the wave function, that is still indicative of high probability because when squared, it would flip up and become a peak just like the other ones. So that's one thing I wanted to talk about with regard to the wave function. The other thing in this case particularly was that the value of k would be this, and ultimately we also have to come up with a restriction on the integer. We have to come up with a quantized restriction on the k value. All right. The quantized restriction on the k value comes about because of this forcing of the wave function to be 0 at the ends. Okay. So if, for example, you say, okay, well, we know when it's at 0. When you're looking at this point here, say this is x equals 0, and this is x equals L. We knew that when we were here, we had a 0 wave function because we were at 0 due to the infinity in potential over here. And this is what killed off the cosine part of our proposed solution. When we get over here, what ends up happening is that we need psi of x equals L to be 0. And what that means is that if I look at a times sine kx, now naturally a could be 0, but that means we don't really have anything at all. There's no particle in the well, so that's not a useful way to do it. But what is a useful way to do it is to say that k is equal to some multiple of pi such that if I thought of, oops, I should have put L in here for x, because that's where we're evaluating L, right there. So what we're doing then is we're going to force the sign to go to 0 at the x equals L point, and that's going to end up quantizing the values of the k number here, okay? Now, we know from the solution to the Schrodinger equation that the argument of the sign is this square root, because that involves that's the constant that gets pulled out twice when two derivatives happen. And also we're going to find that if we use that condition here, this is a quantized situation. And it gives us information about what the allowed energy spectrum is going to be. In other words, if I take a look at this and solve for the energy values here, these things are going to be little en values, right? I'm going to have E1, E2, E3 based on what n value I choose here. And you can see here that if I solve for that, right, I'm going to have to square everything here, and then I'm going to move the h bar squared and the 2m over. So it's going to look like h bar squared. Well, let me put the n squared out here so that it's not so close in. We're going to have pi squared like so. So in this case, the energy spectrum turns out to be related to the square of the order number. Now, in this case, you could say with fairly high certainty that you had 1, 2, and 3. These were the 1, 2, and 3 states. Here's our ground state, which I typically call the jump rope pattern. And then you go to the 2 state, the 3 state, and what this can easily match up with is the number of bumps in the wave function, right? 1 for 1 bump, 3 for 3 bumps. Easy enough to know. Therefore, the number of bumps in the wave function is indicative of the energy of the particle at that point, right? Because this is ultimately what the energy is, and it's related to n squared. Now, note that in the hydrogen atom, it was 1 divided by n squared, which is what the energy of the particle depended on. In this case, no, there's a ground state energy here, all of this stuff, and then an n squared here. So you can see how the energy would change based on changing things like the mass of the particle, the size of the well, things like that. Okay, so a couple of things that come out of this. I mentioned the peak heights relating to the probability. So in other words, where there are peaks and troughs of the wave function, that's where higher probability exists of things. Now, the more peaks there are, the more energy we're thinking of. Now, this can also be a generalized way of thinking, and it can also come about from de Broglie thinking. Well, I should maybe do it this way, but if you imagine that the momentum is related to the wavelength, smaller and smaller wavelength indicates more and more peaks and troughs in the wave function, right? Which is going to tell us there's larger momentum there. And typically with larger momentum, you're going to realize larger energy as well, okay? But definitely kinetic for sure, all right? So when you think of how the wave function communicates information to us, normally I start off by looking at these two characteristics of the wave function. Number one, the amplitude. Where is the amplitude high and zero and etc.? And number two, the wavelength. How many peaks are there? How closely spaced are they? Are they changing, right? Is it going from small to big or something like that, right? So that is an initial way to start looking at information that the wave function gives you. We can say that this is related to the amplitude of the wave function, and this is kind of related to the wavelength. Well, I mean, the whole entire thing, not just that. So you can get a quick visual on whether or not you're dealing with something that's higher energy or less energy, just based on, look, if I'm looking at something like this, it's got just the one peak in it. If I'm looking at this, this has 3 peaks in it. There's more energy here. And you can just look at the number of peaks and jump straight to, hey, it's got more energy, there's more peaks. The wavelength is shorter, therefore it's higher energy, or it's higher momentum, right? You can bring all of that. I'll say one other thing that's of a bit of note here about the wave function, and it is based on this infinite model. We talked a little bit about that last time, saying, yeah, it's not exactly a physical model, but it's not 100% reproducible the way it stands here, because I can't make infinite potentials. But imagine what would happen if I tried to. Well, I would have a non-infinite potential, which means that I would have some amount whereby this would cut off. So I can change this now from an infinitely high well, or an infinitely high kind of trap, to something that's finite, known as the finite well. How does this change the wave function? Well, if we take a look at this and you say, well, I'm gonna have a wave function here that's gonna fit into this well, okay? And the same things are true. Perhaps u is 0 here and u is equal to some constant u naught up here. But this shelf goes, just consider it to go off to infinity, okay? So one adjustment at a time. I take the infinite height of the thing and reduce it to something finite, but I still need it to go out to infinity on either end. If I now try to put a particle in here, what's the difference in the wave function going to be such that I want to be able to look at it and recognize, oh, I've got one of these, or I've got one of these, okay? Notice, in this case, with the infinite well, we talked about the idea that the wave function has to go to 0. In these regions out here and out here, where the potential energy is 0, where the potential energy is infinity, there's no way the particle can exist out there. So I would expect a 0 probability of finding the particle anywhere in these regions here or here on either side of the trap. So the particle must be in here, but I have to connect the wave function with the 0 out here and the 0 out here. That's why we're forcing the wave function to be 0 at the ends of the well. That is, perhaps you can see, not going to be the case here because this is not infinity. So there should be some probability of the particle existing outside, right, of the well. I mean, or perhaps maybe a better way to think of it is it's not necessarily a probability of thinking out of being out there. It's that unless you have an infinite potential, the particle is going to kind of try its best to see, well, what's out here? Right? Imagine it's just kind of trying to figure out, hey, can I do something here? And the answer ultimately is no, you can't. You can't violate energy conservation. If I dropped you in the well and your energy, the total energy of that particle is less than this, I can't find that out here. It doesn't suddenly gain energy from somewhere, right? But what will happen is the wave function is going to explore a little bit more. You cannot force the wave function to be 0 at the ends of the well anymore. So when you look at the first state, if I just extend this down here so I can draw some wave functions for you here. If I examine what is going to be the ground state, what's going to be the analogy to this in the finite well case? I mean, I could show you this mathematically, but it doesn't really matter quite so much. You're going to find that it does the same basic thing. But there's going to be a slight difference because now I don't have an infinite potential, so I can't force the wave function to be 0 immediately upon leaving the well here. You will end up finding that it's going to tail off like that. There are going to be these small tails in the wave function here where the particle's the wave function is exploring, right? It knows it's going to be 0. It knows it has to go to 0, but it's wondering, well, how far can I go? Right? Can I do anything? The answer is ultimately no, you cannot do anything. But it's almost as if it's just having a walkabout. It's having a sniff in here, saying, "Oh, is there something can I get out here somewhere?" Now, it's this phenomenon here which leads to a very interesting situation where you could possibly imagine having a potential which is finite, but this side, which remember when I constructed this, I said these go out to infinity on either side. Well, bring one side way in so that this isn't going to happen at infinity. It's going to just have a little, barrier in the middle, right? So it's almost as if you could imagine putting a barrier in the middle of something like this, right? I could do that. Imagine that I take this situation and I bring it in, and I have a situation that looks like, I'm going to take this down a little bit here. Like that. Well, it was supposed to be kind of more in the middle, but okay, no big deal. What happens if I have a situation like this? I have a well, but it's got a division in the middle of it. And the division of the barrier here is low enough such that the particle could exist in the well, but above this, right? So it should be able to cross from one side to another without without violating energy conservation, yet still remain within the well. Okay. Well, in this case, I'm going to have to adjust my wave function a little bit, but notice that if the energy of the particle is below this barrier, okay, what's going to happen is this same kind of exponential tailing is going to start happening when the wave function reaches this barrier here, okay? What that means is, so let's take a look here. I got that. Let's just re-sketch this out here. So what this is going to mean is that I've got this, it might come down like this, and then I'm going to look at the barrier itself as being that big. And I can, for instance, also find the particle over here. And I need to turn this around quickly here. Oh, I need to get this a little bit further. This has to go a little bit further down. So I'm trying to think about approximately where the zero of the wave function is. It's going to be lined up out here and out here. And you'll notice that here, it's not reaching down 100% towards zero, right? It's not all the way down there. There's a little bit there. But nonetheless, what does this mean? Well, what this means is I'm able to connect the wave functions such that if I start a particle in here and it has an energy below the barrier, it's down in here somewhere, and I'm measuring where it is, I should expect to find it over here at some point. In other words, this wave function has extended into the barrier enough such that it didn't go to zero, it caught the other wave function, which is right next door, and it linked up to it, okay? And then what happens is that if you put the particle in here and it's got a low energy, a low total energy, such that classically there would be no way of this particle getting out and coming out and over, because that violates energy conservation. And ultimately that's what happens here too. It doesn't go over the barrier. It doesn't have enough energy. The energy level's down here. What it does do though is called tunneling. It tunnels kind of past the barrier. I don't want to say it goes through the barrier. It definitely does not go over the barrier. But somehow you put a particle in here and then you measure it and find it over here. And this is the phenomenon known as tunneling. Like so. And before you dismiss this as a quirky offshoot of no real importance, there are whole devices based on tunneling, based on the ability of particles to tunnel, and they do so in a well understood way. And when I say well understood, I mean, in other words, we can calculate everything we need to know about this situation, and ultimately it reproduces what is happening, okay? As to how it is happening, well, we don't really have a good understanding of that. And so it really kind of comes up against this idea of, well, you put it in there and it shows up over here. So the question of how did it get over there, you can't really ever expect to answer that question. Remember, this is not Newtonian physics where if I put something over here, I should be able to track its position as a function of time for the rest of whatever. That's not how this goes. You put something over here, you let the wave function kind of come to an equilibrium here. And if you measure, where is it here, you'll find it in both places. I mean, not at the same time. You'll find it over here, and then maybe you wait a little while, and then you'll find it over here. So the question of how did it get there, we don't have any way of answering that question, because you can't measure and find it in here. That would violate energy conservation. So the particle will never be in here, but it went from there and it appeared over here. And it did so, I mean, I guess I don't want to say instantaneously, because we do have a light speed issue, but essentially it happened like, yeah, particle was there and now it's over here. And there you go. You will also be able to see this happening. This tunneling effect happens at a really nice description of this happens at total internal reflection. So when you take light and it's totally internally reflecting at the boundary of a piece of acrylic and air, like we had in the labs, right? If you snug up, so suppose light's internally reflecting right here off the back of my hand right here. If I take another piece of plastic and I get it really close to this one, all of a sudden I'll pick up a light ray and it will be propagating within this plastic. Ultimately, it's doing exactly this, where the barrier was set by air, right? The air is causing the barrier between the two materials. So another situation where tunneling happens, and this time with light. Anyway, so the takeaway pieces here that I'd like you to consider, I wrote here in terms of when you look at what the wave function is telling you, examine the amplitude, and that tells you probability. Examine the wavelength, that tells you about the energy, and then look at the tails. Is it a straight down to zero? Like, is it right? Bam! Is it stopping at zero? Or, because that would be this kind of infinite well, or does it have these tails on it, right? Does it have those types of tails on it right there? Then it's a finite well, where the restriction on forcing the wave function to zero at the edges is not happening, okay? So, those are the basic three things I want you to be able to look at when you see a wave function and be able to analyze those, okay? All right, so at this point then, let's go talk a little bit about some nuclear physics. I want to talk about some radioactive decay. When it comes to homework set 7, I want to be able to have you answer the questions on what the ultimate ending result of a radioactive decay is going to be. But then there are also a last couple of questions involving calculate the energies. I'm not worried about those, so just forget about those, where it says calculate the energy of the alpha in one of those radioactive decays. Those ones where you're calculating energies, we're not going to do those. But the previous ones where it's what's the result of this decay, that's what I want to talk about right now. So let's take a look here. Let's take a quick look, and and let's go ahead and do this. So if I think about radioactive decay, then there are three modes of characteristic decay that happen. That's not to say that they happen individually. One only ever happens this way, or one, right? They can all happen. It's just that these are three typical ones that we see repeatedly, all right? And when they first discovered them, of course, they didn't know what they were, so they labeled them alpha, beta, and gamma. Which, as you probably know, are the first three letters of the Greek alphabet. And the reason that they did that is because X, the unknown, was already taken through X-rays. So they said, oh, we have to find something different. So there you go. These are the three characteristic decays. And I'm going to just tell you what these are so that when we go to saying, hey, something's decaying via this mode, then you know how to look at the periodic table and go, oh, well, what's happening is this, okay? All right, so an alpha is a nucleus of helium. In other words, it's 2 protons plus 2 neutrons. So 2 p pluses, 2 n naughts. Very heavy nuclei will often spit these out, and it's a great way for them to quickly reduce a lot of turmoil in the nucleus because it gets rid of a lot of material quickly. All right. These were the things that Rutherford used in his nuclear experiment, the scattering experiment I was telling you about. He was firing things at the gold film, the gold foil. He was firing alphas, and he probably didn't know how they came about. I mean, because if he did, he would already know what the nucleus was looking like. But he knew that he had a supply of these things, and he could basically treat them like well, the way I think about that experiment is if you you go into a room with a bunch of billiard ball tables, and then someone puts, balls around on the table and then shuts the lights out so you can't see anything. And then they give you, for example, the cue ball or something, and they say, find where on the table the billiard balls are. Right? So how are you going to do it? Well, if you do it systematically, you start at one side of the billiard ball table and you take your cue ball and you kind of roll it that way, and it hits the boundary and comes back, and you go, oh, I missed. Nothing's here. So I'm going to move to this one. I'm going to do the same thing. Clink. Oh, there goes one. Right? And then hopefully you can find out where the cue ball went, grab it, go to the next one, roll it again. Oh, missed. Oh, nothing happening there. Oh, clunk, 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 clunk. Right? Okay, there's a bunch right over here. So that's basically what you're using the alpha to do. You're basically using it to probe the structure of the nucleus, or that's what he was doing. I don't think maybe that's what you're doing. Therefore, if something undergoes helium, or I should say alpha decay, then what happens is it ejects 2 of its protons and 2 neutrons, but those don't count in the periodic table reckoning. And therefore they move down 2 spaces, or they move 2 lower spaces. So if, for example, you had uranium, oh man, I totally blanked on the number. It's 243, but anyways, whatever it is. You have uranium, and it undergoes an alpha decay. Uranium's number 92. That means it's now going to be element number 90, which is thorium. And the same thing would happen with, going from radium to radon, 87 to 85. Anyways, whatever they are, you're going down 2 spaces. Your element is now 2 spaces less, okay, on the periodic table. So typically that means moving to the left, but of course, if you were already way over here, that means you're coming all the way back over here and you're wrapping around and going that way. So this ends you up. Should I say they lose 2 spaces? beta decay. The beta decay has actually two modes. It has the positive and the negative. And beta negative is just the emission of an electron. Okay? This is an electron. Whereas the beta positive is a positron, antimatter. Right? This is the antimatter electron. And you know when you get those because they hit an electron really quickly and give off photons. And those photons you can detect very quickly and easily. So the positron is emitted or the electron is emitted, and this alters where the element is on the periodic table because ultimately what's going on? In these situations, this is a decay of either a proton or a neutron. So let's just examine this. If I think about a proton, here's proton decay. Proton decay is a proton turning into a neutron. Okay? So a proton can decay into a neutron and become a neutron, but it does have to conserve electrical charge. And you can't just have positive charge and then not, as far as we know. Therefore, it's going to emit a positively charged electron. And it's also going to emit a neutrino, but I'm just going to say we don't really care about that right now. Okay? So this is beta positive decay. Beta negative decay is the opposite. It's a neutron decay, where I have a neutron which then has no positive charge, creating positive charge by becoming a proton. It can't have just positive charge emanating out of nowhere, so it has to cancel it out by kicking out an electron at the same time, plus an antineutrino. Which usually looks like this or that. When you have the bar over the top, that means antiparticle. These things are really interesting little beasts. They're basically as close to nothing as anything can be, but still be something. They travel at near light speeds, which tells you that they're almost nothing, because only light, only massless particles can travel at light speed, right? Like photons. These things are pretty close. They travel at pretty close fractions of light speed. And they're really, really low energy. So they don't interact with very much. In fact, they only interact via these modes. So you can actually cause neutrinos to, you can get neutrinos to cause one of these to happen if you do it right. But anyways, that's maybe a story for another day. Now, when you do this is going to be how you can detect where the element will end up on the periodic table. So if a proton becomes a neutron, that means you've lost a proton, right? You've gone down one on the periodic table. This is beta positive decay, so this is lose one spot, or lose one space. So you have, if you are, I gotta think of a couple of elements which are right next to each other. I don't know ones that are right next to each other. Okay, how about plutonium? If you're plutonium, you're element 94, and if you undergo beta positive decay, then you become neptunium, which is 93. Yeah. Because you've changed a proton into a neutron. So you are not number 94 anymore. You're 93 now because you got an extra neutron. If you are if you are decaying via beta negative decay, you're ejecting an electron, but what's really happening is you're creating a proton within the nucleus, which means you're going up one space to the right. So this is kind of the opposite, right? This is gain one space. That means if you were uranium, which is 92, and you decayed via beta negative, you would now be 93, which is plutonium, neptunium. And then you could do it again and become plutonium. And in fact, I think that something similar happens to plutonium. It's possible that it can undergo 2 beta positive decays and become uranium, and then it's still nuclear fuel, so you can still put it into the nuclear reactors. I forget exactly, but anyways, yeah, that's fun stuff. Last one here is the gamma. Gamma is, if you recall the spectrum, the gamma is the high energy photon, right? This is just electromagnetic radiation. It's electromagnetic radiation. In other words, this is a nucleus that is in an excited state and is decaying, or I don't know if decaying, but sure, it's decaying by dropping 1 level down to its ground state and then ejecting up gamma. The way I think of this is it's exactly what an electron would do inside the Bohr model of hydrogen, right? It goes from state 2 to state 1 by kicking out a 10.2 eV photon, right? The nucleus does basically the same thing. The nucleus, at least the way I conceive of it in my head, it has energy levels, just like an atom, right? Electrons in an atom have energy levels, and the nucleus does too. So if it's in an excited state, it's going to decay, but instead of giving off a photon, like a UV photon or a visible photon, it's going to be an X-ray photon or a gamma ray photon. Right? This is a lot more energy because the nucleus has a lot more energy to get rid of. The nucleus has an immense amount of energy in a very, very, very tiny volume of space. And inherently, that's interesting because when you tap on it or disturb it somehow, that they fall apart. And then they release a huge amount of energy relatively, right? Not like we're going to be going like, wow. But if you have a whole bunch of them, it will blow stuff up, right? As you probably know. So anyway, the gamma is basically the nuclear counterpart to a photon as an electron changes energy levels in a Bohr model. It's exactly the same thing that goes on with the nucleus. So since there is no charge carried by the gamma, it's just electromagnetic radiation, and therefore it does not make any change to where you are on the periodic table. And in that sense, it's kind of nice because we have not total symmetry, but we have the ability to move down the periodic table. We can move up the periodic table, or we can stay right where we are, right? It's kind of like win, lose, or draw. No change in the space on the periodic table. So, for example, you would see this as something like if I just said, oh, I'm going to have uranium, say 235. If I'm going to have uranium 235, I forget where all the things are supposed to go. And it's in an excited state. Normally you'll find a little star by it. There'll be a star. And so what will happen is you'll get uranium 235 plus gamma. And that's going to be its decay. It hasn't changed anything. All right. Here in these cases, we can probably come up with a couple of interesting ones. So we can say U235 becomes what plus alpha? Well, if I'm looking for, well, what's it going to become? Question mark? Well, I know that uranium has 92 protons. You may not, but you can look it up and realize that it does. So I'm going to have 92 protons, 235 protons plus neutrons. And therefore, what I'm going to get here when it decays via alpha is going to be element number 90, which, as I said before, I believe is thorium. And it's going to be 231 because that's going to be the loss of 4 total things from the nucleus, right? 2 protons, 2 neutrons are now gone. So it has a grand total of 4 fewer things in the nucleus. All right. Again, I don't recall whether this is the correct way of writing the number convention here, but the idea is that the 2 numbers tell you, number 1, how many protons are in the nucleus. That's the 92 number. 235 is the number of protons plus the number of neutrons. Okay, so it's like the total atomic number, or the total, I don't know what you call these things. Anyway, this is that's the atomic number, and that's the, so yeah, I don't know, whatever you call them. This is the number of protons. That's what I'm just going to put here, number of protons. And this is the number of protons plus neutrons. Is that one, all right? When you're doing these, then you just go, oh, all I'm doing is I'm making adjustments to the numbers based on what's going on. How do I know it's this? Well, because I know ultimately that an alpha is a 2,4. In other words, there's 2 protons with 4 total things, and that's, yeah, right? Now, see how it all adds up nicely now? Perfect, okay? So the same basic thing happens with the beta decays. They go kind of via this type of thinking, where if I said, if I said I have 235 uranium, and suppose it's decaying via beta positive, what I would do then is I would say, well, it's going to neptunium. No, sorry, it's going, oh, I don't know what 91 is. If I'm going positive, I got to go down 1. Crap, I already wrote that. Okay, time to change and make it plutonium. There we go. So we're going to do plutonium 94, because that's one that I know a little better. And we'll say this is 241. So again, number of protons plus neutrons on the top, and then just number of protons on the bottom. If it's decaying via beta positive, that means it's dropping down 1 space and becoming neptunium. That means you know it's becoming 93. But notice that the actual number of total things in the nucleus has not changed. I had 94 protons and 241 total things in the nucleus. And now I've got 93 of these. You go, oh, well, I've changed this. No, you haven't. You've just changed one of these into another thing, but it still fits into that apple cart. So this number doesn't actually change. Okay, this number is still 241. And then you're just going to say it's going to be plus that plus this. Because this is the positron that comes getting kicked out here due to charge conservation, and then that's the neutrino that goes along with the whole shebang. And whether or not you put that in, I'm not really too worried about it. The opposite happens when you're talking about beta negative decay. You just write it the exact opposite, right? I would have started with this thing over here, and I would have ended with that thing over there, and this would have become an E minus, okay? So you do this. Like so. All right, so that's what examples I have for you here. That's what it looks like when you write these things out. Hopefully I got neptunium correct. I think it is the planet series when you go from uranium to plutonium. All right. I'm going to leave you with a couple of thoughts about beta decay. Beta decay, so you write these types of reactions down, and people think that a proton, if you then like, I don't know, for lack of a better type of visualization technique, if I'm going to bust open a proton to see what it's made of, right, I'm going to go, chunk, 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 right, like a coconut. Whoa, is it made of a neutron plus an anti-electron here, plus a neutrino? No, that's not what it's made of. It's what it's giving off, right? It's not really what the proton is made of, though. So I think what's one thing that I would like to stress here is that the positron and the electron, when these things are coming out of these reactions, they are not emitted. They are not particles that are emitted by this explosion, if you like, or by this transfiguration of one particle into another. The electron, for example, here is created by E equals mc squared on the spot by the leftover energy of this decaying into that. The electron does not get emitted by this process. It is created and then pushed with a large amount of kinetic energy, right? It's like there's a certain amount of energy left over when a neutron becomes a proton. That energy becomes mass energy and kinetic energy, and it gets rid of it. So same thing's going on here. It becomes mass energy and kinetic energy, okay? So that it kicks the particle away. I just don't want to leave you with the idea that these came from within their respective particles somehow. The electron was not contained within the neutron. It is not, that is not. That's a big no, okay? They are created on the spot. No electrons exist in the nucleus. They can't, right? And if you think that they can, check it with the uncertainty principle, right? In other words, the uncertainty principle is telling us that the radius of a nucleus, which would be 10 to the minus 15th meters, is going to cause the electron to be so uncertain in its velocity that even if it was in there for a small amount of time, it's not anymore, because the uncertainty in the velocity is huge, right? And you'll find that it's going to be almost 10% light speed or something like that, just the uncertainty. Okay, so even if you thought you had an electron confined in the nucleus, you're not going to for very long. Right? Okay, so that's a little bit on nuclear physics and how to recognize what the end result is. Nothing more than that. So last things I want to do here then are talk a little bit about some mentalities, maybe some study tips for the final. We started this a long time ago. It seems like fully 15 weeks ago. And I chose to start with optics because I felt like it was the best way for you to get your hands on diagrams that can be useful, and getting your hands on diagrams that are useful in an easy way. So the number one thing that I'm going to tell you is practice your diagrams. Thinking about what we did in optics, thinking about what we did in thermo, thinking about what we did in special relativity, what we've got going on with wave function diagrams here. So just thinking about visualization and how to represent it, okay? Ultimately, and I want to make this as clear as I can, ultimately, you have to communicate your understanding to me. And if I'm not able to follow it, then it's, maybe you understand it really well, but if you can't communicate it in such a way that I can figure out what you're talking about, it's hard to get a good outcome from that. So that's why the diagram is almost always the easiest, quickest thing to do. Draw one of those, and I go, oh, look at that. I can see that from this and this and this, right? This is how this looks. Okay, you know what you're doing. Great. And then you can move on. I highly suggest not jumping straight to calculations. Here's one other thing that I think many of you do need to be aware of. You are using a different sign convention for the first law, thermodynamics first law. I noticed many of you on problem 1 on the second celebration, and also problem 3, you're looking at the wrong signs for the work. I would definitely recommend get those straight, okay? Figure out what is going on with that, because I didn't teach the way you're doing it, so I would suggest rethinking that. Other than that, the final for me does 2 things. It's a look back from optics and thermo, sections 1 and 2. So it's a review of those, and then it's also a celebration on all the stuff since the number 2. So that's since thermal, in other words, the special relativity and the quantum mechanical stuff that we've been doing. That quantum mechanical stuff, like you see on the homework, includes things like the photoelectric effect, Compton scattering. We just talked about radioactive decay. A little bit on the Bohr atom, the Schrodinger equation, and the wave function stuff like that. So look through the homework, feel solid on those problems, and go on in and have a good time. After all, it's a celebration. So it will be up and running next Wednesday. So mark your calendar and try not to be late for it. So other than that, I don't think I have anything else to say other than I never really know how well stuff like this has gone, but if you've been watching for the whole semester, thanks. Appreciate your attention, and thanks for your hard work. I know a lot of you have done a lot of work in this class, and I appreciate that. And I will, I guess, bid you good luck going forwards. And if you have questions, go ahead and fire me an email. After that, enjoy a summer break, and good luck with your next steps, whatever they do or wherever they may lead you. May you have good energy and happy, warm winds behind you.